Hello and welcome back. Today we're going to begin a discussion on the idea or the concept of superposition. Now, superposition is a concept that we use quite a bit in electrical and computer engineering, and it's a wonderful, powerful concept, but it can be applied to circuits, and that's what we're going to do here. Now, as a circuit solution technique, superposition is not terribly efficient, but the idea of superposition is used all the time. Superposition is a algorithm or an idea that says we're going to divide and conquer a problem. So in our particular case applied to circuits, let's say we have a complex circuit, a very complicated circuit topology, and we're looking for a voltage or a current. And so superposition says instead of finding that voltage or current of this complex circuit topology using nodal analysis or mesh analysis or something like that, we are going to take our problem and we're going to break it into a bunch of smaller problems. Hopefully these smaller problems are simpler, and we will find some answers in the smaller, simpler problems, and they can be combined back together to give us the answer to the big problem that we wanted originally. So more formally, superposition says this, that if you're looking for a current, for instance, this also applies to voltage, but if you're looking for a current in a circuit that contains linear circuit elements and multiple sources, then you may find the current you're looking for by finding that current due to each source acting alone, and then once you find these currents due to each source acting alone, we are going to add them all up. So instead of finding the single current in the large complicated circuit that we're looking for, we are going to break it into a bunch of smaller problems, find that same current due to each source, only one source acting at a time, find that current, and then all of those currents can be added together to find the answer we want. So as more of a recipe or an algorithm for you, this is how we are going to apply superposition to circuits. Circuits is, first thing we're going to do is we're going to find the number of uncontrolled or independent sources in our circuit. Now remember, this is going to be uncontrolled independent. These are the sources that have a round circuit symbol, all right? Not the diamond-shaped ones, but the round ones. So determine how many of those we have in our circuit. And then we are going to kill all the sources except one. Kill all the sources except one. And what do we mean by kill? When we say when we want to kill something, what we mean is make it zero valued. So a voltage source, when you kill it, becomes a 0 volt voltage source. A 0 volt voltage source is also called a short. If it's a current source, we make it 0 valued. It's a 0 amp source. That is also called an open. So once we've killed all the sources except for one, then we are going to find the quantity or the response of interest. So if we're looking for a current, we're going to find that current, but this is a different circuit. There's only one source being active. So we're going to find the quantity that we're looking for. And then what we're going to do is we're going to repeat step 2 over and over and over again, and we're going to do it over and over and over again for each of the uncontrolled sources. So we're going to solve the circuit looking for the current, for instance, that we want, and we're going to do it for only one source active at a time. And so what we're finding is the current due to each source acting alone. And then the theory of superposition says once we've done all that, we can just sum together all these individual sub-responses, these currents that we found on these little problems, sum them together, and that will be the answer we're looking for. So it's an idea that basically says we are going to take the problem and we're going to divide it into smaller problems, and it's a divide and conquer scheme. It's a wonderful, powerful idea, and we use it all the time and refer to it to make our life easier, to give us insight into problems. As a circuit analysis technique, it's not necessarily the most efficient sometimes, because what it means is you end up solving a bunch of little problems. Sometimes the little problems aren't so little. So as a circuit analysis technique, it's sometimes not the best, but it's a powerful idea that we'll use over and over again in ECE. Now notice that there is a requirement that superposition only applies to linear circuits. Let's do an example. I think it's the most straightforward way to get an understanding of what's going on. So here's a circuit, and we've looked at this one before. We saw this one back when we did mesh analysis. And just kind of as a reminder, you can go back and watch that video again. But in mesh analysis, remember, we define our mesh currents consistently. And so in this problem, we defined I1 and I2. And back in that video, if you go watch it, you'll discover that we found that I1 was 6 amperes and I2 is 4 amperes. And if you go back and refresh your memory, what we really were looking for in that problem was we wanted to find the current in the 3 ohm resistor because we were, I think, trying to find the power in that resistor. And in this case, of course, the current in the 3 ohm resistor, well, we have the I1 current going down, 6 amps, and then it's being offset by the I2 current, which is going up, which is 4 amperes. And we saw back in mesh analysis that the current in the 3 ohm resistor is 2 amperes. And so what we'd like to do is we'd like to look at this circuit again, and let's try to solve for this current in the 3 ohm resistor using superposition instead of using mesh analysis. So we'll get the same answer, but we're just going to basically work the problem again a different way. So we're looking for the answer of 2 amperes. All right, so to get started, remember step 1 is, in superposition, is to determine how many independent or uncontrolled sources we have. And we see here that we have a 10 volt voltage source, plus to minus, and over here we have a voltage source, remember, that's plus to minus this way. And so we see in this circuit we have 2 uncontrolled or 2 independent voltage sources. So I expect to work this problem, to solve this problem I need to work 2 smaller problems and then find those answers and combine them together. So let's get started. So we need to kill all the sources but one. So we only have 2 sources, so let's kill the 10 volt source. And what do we mean by kill the 10 volt source? Well, we're going to take the 10 volts and we're going to make it 0 volts. And what do you get when you have a 0 volt source? Well, something with no voltage across it is simply going to be a short. And so the wire gets put there in place of the 10 volt source, and we have shorted out the 10 volt source and killed it, and this is the circuit we have left. So if we redraw the circuit, you see we have this. And again, keep in mind what we're after. Ultimately, we're looking for this current right there. That's what we want. And so this is a different circuit, so we'll call this I3A. This is the current in the 3 ohm resistor, and we'll put an A because we'll call this, the A problem, the sub-problem A. And then how do we find I3A? Well, let's back up and let's find this current right there. And we'll call that simply I42A. All right, so I42A, it's the current from the 42 volt source, A because it's the A sub-problem. What is that current? Well, we have a 42 volt voltage source, and what resistance does the 42 voltage source see? Well, it sees 3 is in parallel with 4, and all that is going to be in series with 6. And so when you take 6 series 3 parallel 4, you'll find that works out to be about 7.7 ohms, which means we have 5.44 amperes for I42A. So this current right there is 5.44 amperes. But when the I42A current gets to this node, we then now have current division. Some of the current goes this way, and some of the current will go that way. And we are interested in finding I3A. I want to know how much current goes down through the 3 ohm resistor. So I3A is going to be current division. Well, what is current division? It's 5.44 amperes. And that current is being divided between what? Between the 4 ohm resistor and the 3 ohm resistor. So I get 3 plus 4 in the denominator. And remember, in current division, if I'm looking for the current in the 3 ohm resistor, the numerator needs the other resistor. So that's 4 ohms goes up there. And I3A will be 3.11 amperes. Okay, so now we found the current in the 3 ohm resistor, because that's what we want, due to the 42 volt voltage source acting alone. That is the A problem. So let's kill the 42 volt voltage source. By killing it, we get a short, as we see over here, and let's turn the 10 volt voltage source back on again, and we'll call this subcircuit B. And again, what are we looking for? Well, we're looking for this current right there. So we'll call this I3, and we'll call it I3B. It's the I3 current in the B circuit, and it's the sub-response we need. So how do we get I3B? Well, let's look at the source. It works pretty much the same as the last one. We have a 10 volt voltage source, so there's going to be a current flowing this direction. We'll call this I10B. And what is I10B? And I have the arrow drawn right. The energy is going to this side's higher than energy than this side, so the current will indeed flow in this direction. You can go with the passive sign convention and verify that. But I10B is going to be the 10-volt source, and what kind of resistance does it see? Well, it sees 6 parallel 3, and that's going to be in series with the 4. And then when you compute that, you will find that that's going to be 6 ohms, and so you'll get the answer of 5/3 ampere, and that's I10B. So the current going to the left here is going to be 5/3 ampere. Well, what we want is the current going down this way in the 3 ohm resistor. So I3B, well, we see the direction of I3B opposes I10B, so I know there's going to be a minus sign. And in its current division, the 5/3 ampere is going to be divided, and it's going to be divided between the 6 ohm resistor and the 3 ohm resistor. And for current division, I need to stick the 6 on top. And when you do this, you'll find that I3B is minus 1.11 ampere. So now we have just found the current I3A. We have the current that's going down through the 3 ohm resistor. We have found the current going down to the 3 ohm resistor in these two sub-problems. This is the yellow current over here on the left is the current due to the 42 volt source acting alone. The purple current over here on the right is the current due to the 10 volt source acting alone. And then superposition tells us that I can find I3, that is the current, the true current in the 3 ohm resistor. This is the back on the original problem. I'm looking for this current right there. I can find that current. That current will simply be the sum of our two sub-responses. So we get 3.11 amperes due to the 42 volt source, and then I'm going to add to that a minus 1.11 amperes due to the 10 volt source acting alone. And we see when we do that arithmetic, we'll find the answer is 2 amperes. The current going down in the original problem is 2 amperes, as we already knew. Superposition says that I can find the response that I want. I can find the response that I want due to each, finding that same response due to each source acting alone and simply summing them up. Superposition. Again, not the most efficient circuit solution technique, but it is a wonderful, powerful idea. And for these simple circuits like we have in some of these video lectures, superposition can be quite fast, because when you start killing the sources, then the circuits do get quite a bit simpler. Let's do another example. So here we have another circuit, and I believe we saw this in the super mesh video. And in this particular circuit, we'd be interested in finding, let's just find the exact same things. In the super mesh video, we found I1, and then we looked for I2, and after we did the analysis, we found that I1 was 4 amperes and I2 is 7 amperes. So let's go and find those same two numbers again, but let's just do superposition. So the first step in superposition is to figure out how many independent or uncontrolled sources we have. And in this case, we see we have 3. We got a 42 volt voltage source, we have a 3 amp current source, and we have a 10 volt voltage source. So we have 3 independent or uncontrolled sources. So I expect to work this problem 3 times, add up 3 numbers, and get the answers 4 amps and 7 amps in the end. So we need to kill each source, kill all the sources but one. So in the first case, we will kill the 3 amp source, and we will kill the 10 volt source. And as we previously saw, if you kill a 10 volt source, what you're really doing is you're making it 0 volts. And to make it 0 volts means you are going to short it out and it becomes a wire. And if we're going to kill a current source, when we kill it, we're going to make it a 0 amp source. And if you're a 0 amp source, then what you do is there's going to be no current. It becomes an open. It's like it's not even there and the wire has been cut. It's a 0 amp source. So let's redraw this. So taking the circuit and redrawing it, killing the 10 volt voltage source, we do indeed see the short, and killing the 3 amp current source, we indeed see the open here. And so again, we were looking for this current, we'll call that I1A, and we're looking for this current, I2A. So this is the I1 current and the I2 current due to the first source, the 42 volt source. And we'll see in this case I1A must equal I2A because they're in series, which is going to be 42 volts, and the 42 volts sees simply 6 in series with 4, which is going to be 10 ohms. And we see we got 4.2 amperes for both of those. Killing the 42 volt source turns it into a short, and we see that here on the left hand side of the second circuit. Turn on the 3 amp source, so we put it back in right there, and then the 10 volt voltage source stays killed, which means it also stays to be a short. And so again, we're looking for this current. We'll call this I1B, and we're looking for this current. We'll call this I2B. It's the B circuits for. So I1B. We can see we got it in the middle circuit, a beautiful textbook example of current division. We have the 3 amp source, and it's being divided. It's being divided between a 6 and a 4 ohm resistor. And for I1B, we see the arrows going the wrong direction, so we need a minus sign. And if I'm looking for the current going in the 6 ohm resistor, I need to stick the 4 ohm resistor on top. And so when you do this, you'll find you have negative 1.2 amperes. And then I2B, again, textbook current division. We have a 3 amp source. It's being current divided, and it's being divided between 6 and 4 ohms. And if I'm looking for the current in the 4 ohm resistor, then it needs to be 6 ohms on top. And then we discover we have 1.8 amperes. So the contribution to the I1 current due to the 3 amp source acting alone is negative 1.2 amperes. And the contribution to I2 from the 3 amp source acting alone is 1.8 amperes. And finally, we're going to kill the current source, which then is going to make it an open once again. And this guy remains shorted out. And then we'll turn the 10 volt source on, and this is the circuit we have. Once again, remember, we're looking for this current, and we're looking for this current. We'll call this guy I1C, and we'll call this guy I2C. And we see that I1C and I2C are equal to each other. And the current's going to simply flow around this direction, passive sign convention. And how much current flows? It's going to be 10 volts, and it's being divided among 6 and 4 in series, which is 10 ohms, and we get 1 ampere. So now we can use superposition. We found each of the currents, I1 and I2, due to each source acting alone, and superposition says we can now find the answer we're looking for. And I1, the total I1, is going to be I1A plus I1B plus I1C. I1A is 4.2 amperes. I1B is plus minus 1.2 amperes, and I1C is 1 ampere. And add those all together, and we find that I1, the total current in the original circuit, I1, that is the current flowing around this way, I1 in the original circuit on the previous page is going to be 4 amperes. And then I2 is going to be I2A plus I2B plus I2C, and adding those up, we have 4.2 amperes plus 1.8 amperes plus 1 ampere, and you add those up, and you'll find that I2, the total I2 current in the original circuit, is 7 amperes. And if you take the numbers here, 4 amperes and 7 amperes, and go back and compare it to the solution we got from mesh analysis in the previous video, and for the super mesh, 4 amperes and 7 amperes. Superposition says that you can get any number you want, in this case the two currents I1 and I2, and you can find them by finding those same currents due to each source acting alone. Superposition is the concept of dividing and conquering. You can find the answer you want by solving a bunch of little problems. If we have n sources in our circuit, we're going to kill all the sources except one. We're going to find the value I want, and we're going to do that n times. We're going to do this over and over and over again, n times, and then when we find those n sub-responses, we simply add them all up, and that is the answer that we were looking for in the first place. Not the most efficient method sometimes, but it's a wonderful idea that lets us take a problem and break it apart and see kind of what each little source is contributing to the response of the circuit. We'll use superposition, not necessarily as a circuit analysis technique, but we'll use it as an idea to make a problem simpler and easier to get our head wrapped around. And superposition is used over and over again in every aspect of electrical and computer engineering. We'll go back and review this some more. It's a concept that's really powerful. It lets you really have a great deal of insight and understanding, and we'll use it from time to time in our analysis of circuits too. Thanks a lot. See you later next time.